In section 4.5, we're continuing with the multiplication rule and taking a more in-depth look at problems involving complements and conditional probability. Of all the different types of probability problems, I find that my students have the most trouble with problems asking what's the probability that we find at least one of an item has occurred. These types of problems are introduced in this section. First thing to understand, which is going to be pretty logical for most of us, is that when we talk about getting at least one of an item, we're talking about getting one or more of that item. Also, we need to understand what complements are. Remember that an event and its complement, if we add all those things together, they always total 100%, total the full sample space. I have in parentheses here opposite. Okay, that's not quite what a complement is, but that's how we're going to refer to it, meaning that everything that's not in an event is in its complement. Together they total 100%. So the complement of getting at least one of an item is that we get none. If we take all the events where we get at least one and we combine it with the event where we get none of that type of item, that totals every possible situation that could occur, or 100% of the situations. For example, if we're talking about having 3 children, the probability of getting at least one girl is the same of getting one or more girls, so 1, 2, or 3 girls. The complement of that is having no girls, or in other words, all boys. If we take all of these outcomes and we add them together, that covers every possible scenario. Those total 100%. That being said, at least one problems are complement problems. So anytime you read a problem and it's asking what's the probability of getting at least one event occurring, we want to treat this as a complement problem, and we're going to do 1 minus the probability of getting none of that event. So let's actually find the probability of having at least one girl among 3 children. We're going to assume that girls and boys are equally likely. The gender of a child is independent of the gender of any subsequent child. So let's do this the long way first. We'd write out the full sample space. We know that there are 3 children. There's 2 ways to have each child. 2 times 2 times 2. I'm just writing as 2 cubed here. There's 8 different ways that we can have 3 children. We would take this and cut it in half. We get 4. So we write 4 males and 4 females to start. Okay, it's just half of however many there are. After that, we cut it in half again. We get 2 males, 2 females, 2 males, 2 females. And then lastly, the third row, we just alternate. So this goes through every possible way that we can have 3 children. Okay, if we look at all the different ways that we can have at least one female, right, we can see there's at least one in everything except this very top one, where we have no girls. Okay, or in other words, all boys. So rather than have to write out this sample space all the time, we want to use this complement rule to find the probability. The probability of getting at least one girl is 1 minus the probability of this event occurring. Okay, that event is easy to calculate. It's just the probability of getting a boy 3 times. There's a 1/2 chance of getting a boy to the 3rd power, since we want that same event to occur in succession 3 times. So 1 minus, this ends up being 1/8, and that gives us our answer, 7/8. So let's do this problem the same way. You're taking a multiple choice quiz with 4 choices per question. You didn't study, you're going to guess on all the 5 questions on the quiz. What are the chances that you get at least one problem correct? Now, if you actually wanted to write out the sample space for this problem, it would be absurd. Here it is on the right here. Okay, now if we looked at all of these, we can see that we get at least one problem correct in every single one of these, except this very top one up here, where we got every single one of them wrong. W is wrong, C is correct. All right, now obviously you don't want to have to go through the trouble of writing all those out, so instead we'll do this as a complement. Complement of getting, or I'm sorry, the probability of getting at least one correct is 1 minus its complement, or 1 minus this very specific situation here where we get every problem wrong. Okay, so now what's the probability of getting a single question wrong? Well, there's 4 choices per question. 3 of them would be wrong. 1 would be right. So there's a 3 out of 4 chance we get that wrong, and we want to do that with all 5 questions. So 1 minus 3/4 to the 5th power. We just subtract that out. We get our big fraction here, and we'll switch it to a decimal to 3 decimal places. 0.763 is our answer. One more example before moving on. Assume that the probability of a defective Firestone tire is 0.0003. If the retail outlet CarStuff buys 100 of these tires, find the probability that at least one is defective. If the probability is high enough, plans must be made to handle defective tires should they go through the trouble to make those plans. All right, so we want to find the probability that they get at least one defective, and that's going to equal 1 minus the probability that they get none that are defective, or in other words, all the tires are good. Okay, so now the question is, what's the probability that a single tire is actually good? Well, we know that the probability that it's defective is 0.0003. So the probability that it's good is just 1 minus that. And we end up with 0.9997, okay, for a single tire to be good. Now we want that same situation to occur again and again and again 100 times. So we want to do 0.997 to the 100th power, and that's just getting subtracted from 1. Okay, we end up getting 0.0300 as our answer. Right? This is a low enough probability where the company really doesn't have to bother making a plan to deal with defective tires. Conditional probability we've actually spoken about in 2 sections already this chapter. There's actually an equation for conditional probability. It's right here. We want to find the probability of B given A. Okay, it means A has already occurred, so we want to find the probability of B occurring after that. And what we do is we look for the overlap of those two events divided by the given. Given is always on the bottom. A lot of times these problems can be handled logically. That being said, let's look at example 4a. We have our table that we've been working with all chapter. We want to find the probability that we choose a male given that the student has identified as conservative. That being said, we can see that there are 27 students who identify as conservative. Of those, 6 are female, 21 are male. So we can simplify our fraction, 21 over 27 to 0.778. Now we're going to do something called reverse the conditioning. Instead of finding the probability that a student's male given that they're conservative, we want to do the opposite and find the probability that they're conservative given that they're male. This is going to be a different answer, and this is why we have to be careful with these types of problems. Now remember, anytime we're doing a conditional probability problem, the denominator of the fraction is always the given. Okay, so this is telling us we know that the student is male. We want to look at this row here, only the males. So we can see there's 115 males. That's going to be the denominator of a fraction. What's the probability that this randomly selected student is a conservative? Well, there are 21 of those 115 students that are male, 0.183. All right, now let's do a few card problems. I know some students haven't played enough card games to know what's in a standard deck, so I have it all listed out here. To start, there are 52 total cards in a standard deck. That doesn't include the 2 jokers. Half of these cards are red, half are black, so there are 26 of each. There are 4 suits: clubs, spades, diamonds, and hearts. Clubs and spades are black, diamonds and hearts are red. Each of those suits have 13 cards. And those 13 types of cards are listed here. Goes 2 through 10, and then Jack, Queen, King, Ace. When it mentions face cards, it's talking about the Jack, Queen, and King. That's because there's pictures of people on them, hence they have faces on these cards, but not any of the other cards. Obviously, there's 4 of each because there's 1 of each suit, which totals 12 face cards in the deck. All right, so we want to find what's the probability of drawing an ace given that the card is red. So there's 26 red cards. Of those, 2 of them are aces, the diamond, the ace of diamonds, and the ace of hearts. These are both black aces, so they aren't included in that group of 26 red cards. So 2 out of 26 simplifies to 1 over 13. Part B, find the probability of drawing a red card given that the card is an ace. So in this problem, we know that the card is an ace. What's the probability that the card is red? Well, there's 4 aces, so that's going to be the denominator of our problem. Of those 4 aces, 2 of them are red. So 2 over 4, so 1/2 chance, 50% chance of it being red. This next question is about independence. Okay, we can check independence mathematically. We want to see, does a conditional probability of B given A equal the probability, right, without that condition, just the probability of B. So for this problem right here, does our conditional probability of ace given the card is red, is that the same as the probability of just drawing an ace? Right, so if we were to just draw an ace from the deck, there are 4 of them out of the 52 total cards in the deck. That still simplifies to 1 over 13. These two fractions are the same. That means that yes, these are independent. Okay, the conditional probability of ace given that the card is red is equal to the probability of just drawing an ace. If we had done it with this one instead, the probability of drawing a red card, there are 26 red cards out of 52. That's 1/2. Okay, that's the same as the conditional probability of drawing a red card knowing that the card is an ace. Last set of examples, find the probability of drawing a club given that the card is black. So there are 26 black cards, and of those 26 black cards, half of them, or 13 of them, are clubs. Okay, that simplifies to 1/2. Find the probability of drawing a black card given it's a club. 13 cards are clubs. Of those 13 clubs, all of them are black. So this simplifies to 100%. F are the events club and black independent. We can check either of these. Let's say we stuck with this first problem here. All right, so is this probability the same as just the probability of drawing a club? All right, there's 13 clubs out of 52 cards. That simplifies to 1/4. Okay, that's different than this fraction. All right, these are not independent.